Thank you to the organizers for the invitation. It's very nice to be in Lyon. So I'm from Belgium, as I said. I'm from the Laboratory of Acoustics, or it used to be the Laboratory of Acoustics and Thermal Physics, and you will see in the talk that indeed what we are doing is acoustics and thermal physics, and actually that we are using a laser only to heat, to make thermal expansion and to make waves, and that's it. We don't do any sophisticated optics or spectroscopy with laser, at least until now. But okay, recently we had some new colleagues, so the name of the lab now is Soft Matter and Biophysics. But what we are doing is also soft matter, because it's typical when you heat something, expansion, acoustic waves. With acoustic waves you have expansion and compression, so the material needs to be soft. Yeah. Although you will see there is one application on diamond, which is not very soft, but okay, we still call it matter. So the talk is about laser and ultrasound. Some of the aspects have been said already in the previous talks. For example, yesterday we have seen in the talk of Paul Beard that the photoacoustic effect was discovered by Alexander Graham Bell and his colleague Charles Sumner in 1880, where he used sunlight to heat periodically. The sunlight was chopped to make sound. Yeah. And so for that we use actually two effects. The initial effect, okay, three effects. The first effect is optical absorption, which already means that we will have optical information in the signal. Then we have heating, yeah, so we have, and the heating is giving expansion. The heating itself, it's called the photothermal effect. You convert light to heat, and you can measure it in many ways. Typically you are doing it fast, so you need a fast way to detect the temperature changes. But then since you have thermal expansion, and since it's modulated, it's dynamic, you have acoustic waves, you have stress, and the stress is impulsive, so it propagates as acoustic waves. Yesterday, so we've seen the talk where this technique or approach is used to do imaging, yeah, in the technique of photoacoustic tomography. So you flash light on the sample, everything that absorbs is generating acoustic waves, and you are detecting the acoustic waves with transducers here. All the transducers give individual signals, and then by some processing you can reconstruct the image. Processing can be phase array imaging, or it can be time reversal. In any case, you can have quite nice pictures. And the main information that you get is where are the sources, yeah, and also how strong are they. Yeah? So you have optical contrast, because the more absorbing, the more signal you have, but at the same time you have this acoustic spatial resolution. Yeah? We do not do this. Yeah? We use only acoustic waves and heating to get acoustic properties and thermal properties. We are not so interested in optical properties, but still you will see that there are quite some applications. Yeah. Why to use laser? Well, the nice thing about laser light is that you can nicely manipulate it, you can send it where you want, you can make patterns, and that you also have, so that's spatial coding that you are using, but you can also do temporal coding, because the laser pulse can be flashed, can be modulated, it can be noise modulated, periodically modulated. So you have quite some control over the light. And for example, one advantage is that, as you see there in the animation here, that you can make oscillating heating, and so then the heat will stay close to the source, but where does it? Will stay close to the source, and depending on the time scale or the frequency, you can manipulate how deep the heat is going. So you can actually manipulate, if you measure the temperature close to the source, how far you are probing. Yeah? And so that depends on the time scale of the phenomenon. Yeah? So you use time and space, spatial coding to get information, in this case about the thermal properties, because it's the thermal diffusivity that will determine how far the heat is going, how far it is diffusing. At the same time, if you modulate fast enough, you have efficient acoustic excitation, and with that you can make all kinds of acoustic waves. In our lab we are focusing on guided waves, and more in particular surface waves. Surface waves which become plate waves when you have a thin sample. Yeah. And the nice things about surface waves is that, as you can see, that so you excite them at the surface, and they have a certain range of penetration. Yeah? They don't go very deep, but they still go a little bit deep. And the depth that they go, that they penetrate, is actually quite similar to their wavelength. As you can see, the wavelength is about the size of the lateral size of this sample here, and the depth of penetration, so until where it stops, is about the same. So you can use the wavelength, and if you think about waves, wavelength is related to frequency. You can use wavelength or frequency to play with the probed region, yeah? Because the speed of sound, the speed of the waves, will depend on the elastic modulus of the region in the region that you are probing, and so that can be modified. So the take-home message of this slide is that we are using light to make acoustic waves and thermal waves or thermal diffusion at least, to get information about thermal properties and acoustic properties, acoustic modulus. This is the overview of the talk. So I will give a little bit of theory, some equations, mainly if you would ever need them, that they are in the slides and they are a little bit in the movie, and you can use them as a kind of startup to do some calculations. In the back of the slides is also my email address, so you can always write me. So after the theory, I will mainly focus, because okay, it's a summer school, not yet on our applications, but more on how we detect these displacements that are made by the waves, and how we detect the temperature changes. And mainly because the techniques that we are using are optical. Yeah. Because the waves that we are making, they are fast. Yeah, they travel at 3,000 meters per second. The heating can be slow, but still it's nice to have a sensitive technique, interferometric techniques to detect the waves. Yeah. And as you can see here in this list, I will briefly scan through several optical detection techniques. Why so many? Because depending on the type of sample that you have, is always one which is most suitable. Yeah. Sometimes more than one, but it's nice to have like some view that of many. And I will a bit distinguish between detecting displacements at one point and detecting displacements full field with the camera, with some stroboscopic techniques. And after that, if I still have time, I will go to the applications to show, let's say, the relevance of using these techniques in mainly in material science, yes, but many things I think can also be translated to biomedical applications, although we didn't do yet so many. So first, something about the theory of photoacoustics. So as we know that acoustic wave propagation is governed by the acoustic wave equation, which actually is a result of Newton's law and of conservation of mass and of the gas law or Hooke's law, depending on if it's a liquid or a gas or a solid. And those are, and thermal, let's say thermal expansion and thermal diffusion is governed by Fourier's law, yeah, the French Fourier. Those are linear differential equations, and the nice thing, the nice thing is about those equations is that the solutions are sinusoidal functions, yes, and so that's why in my talk now I will distinguish between different kinds of excitation, but I will always start with sinusoidal, because the nice thing is about sinusoidals, you take the derivative and again you have a sinusoidal. You take 2 times the derivative and again you have a sinusoidal. So that's why they actually are solutions of the wave equations, but because the wave equations tell you that the derivatives, time derivative is second order time derivative of the function is the same as or proportional to the second order spatial derivative of the function. So it's nice to have these sinusoidal functions, and then to take these sinusoidal functions together with Fourier transforms to get solutions for general functions. So, and since waves are propagating in space and in time, we have to distinguish between if the wave is sinusoidal in space and in time, or in one of both. Yeah? In the solution I will give you first, I will come to this later. I will first start with sinusoidal in space and in time. Yeah? So as you can see there on in the right movie, the wave is going, or the heating, yeah, the heating pattern, and then the response of the sample is sinusoidal in space, but it's also going up and down sinusoidally at the frequency of interest. Yeah. How we do this in practice? How do we make, so we can exploit this in practice, in practical experiments. We make sinusoidal waves by crossing two laser beams and to create an interference pattern. Sinusoidal in time, for that you cannot use a pulse laser, you need a continuous laser modulated. Yeah? But for now, the main thing I'm speaking about sinusoidal is for the mathematical modeling. Yeah? Here on the top right, I forgot to mention that, but there you see that the heating, which is induced by those two laser beams in the z direction, yes, is actually the derivative, the spatial derivative, the loss of heat, the loss of intensity, according to Beer's law. Yeah? Beer is, I think, English, but Beer is also from Belgium, as you know, just some advertising in between. So we use Beer's law to simulate how the light is actually decaying with space, but actually in the following approximations, usually I will assume that the heating is uniform, actually that the optical absorption is weak. Yeah. In the next step, you can still keep this spatially sinusoidal heating, but use a pulsed laser, use a pulsed excitation, and then the solution looks more like this. So maybe let's wait until the beginning of the movie. Yeah, now we have flashed the sample, yes, and you see two things. Here you look at the displacement. You see that there's a kind of average displacement which in the beginning, yeah, so that's a thermal expansion. And on top of that, because you have crossed laser beams, you have a sinusoidal grating, and you have waves which are moving, you see also some sinusoidal aspect. So that's a nice thing about photothermal and photoacoustic signals, that they have the two in one. Actually the three. They have the optics, optical absorption, they have thermal expansion, they have acoustic waves, and at the end, if you wait long enough, because it's a bit slow, you also have thermal diffusion. So a lot of information in one signal, and even you have acoustic attenuation, so all is there, and you can do really material science. So the two equations that we need are the Fourier equation that describes heat diffusion. Q here is the heat source. The relevant properties of the material are the density, the heat capacity, and the conductivity, thermal conductivity. The heat source, as I said, to make it simple, and because it's also useful in practice, we use sinusoidal in time and in space initially. So, well, if you put a sinusoidal in this equation, you get a sinusoidal. So that's why the temperature, again, here is sinusoidal. Although I think I forgot the term. Oh no, this is the temperature as a function of the frequency. If you look at the temperature as a function of time, there will be also a sinusoidal factor here. So then you put this temperature inside of the acoustic wave equation, this one, yeah, which says that if you have no source, then you know, everybody knows the wave equation. If you have a source, the source is related to the spatial derivative, to the change, to the gradient of the temperature, as you can see here. And an important factor is the thermal expansion coefficient. In this case, it's called gamma. Yeah. But again, since we have sinusoidal solutions, it's very easy to solve it. It's almost to solve it like a normal algebraic equations. Yeah. Then once you have the solution as a function of frequency and which is also sinusoidal in space, yeah, then you can assume, you can take, okay, which source do I have? Yeah? Which combinations of sinusoidal functions do I have? For example, here we take a source, heat source, Q, which is sinusoidal in space, or cosinusoidal, and a delta function in time. So pulse in time, which is a typical experiment we do in our lab. Yeah? And then the nice thing is you just take Fourier transform of this, which is actually not that difficult, and you obtain, in this case, that you have still, of course, your heat source was sinusoidal in space, or your solution is sinusoidal in space, and you have some thermal decay here, exponential decay of the grating. Yeah, this was the exponential decay here of the grating. It doesn't look very exponential because we use a logarithmic time scale, but it's exponential. That's for the temperature, and for the displacement, the same. Displacement is a bit more complicated, so you see many things, many factors. Yes, one is that the solution is proportional to the thermal expansion coefficient and the heat source, Q. Yeah. Another interesting thing is that you have a lot of information about thermal properties. Yeah, there's the thermal diffusivity here. There's the heat capacity. Yeah, in the prefactor, the bigger the heat capacity, the less will be the temperature change, of course. And there is also the acoustics. There's the speed of sound here, yeah, in these cosine functions. And so all the information is there, as we have seen also in the signal. Yeah. Okay, this was the first slide about equations. This is the second slide, or maybe that's 2 out of 3 or something. This is just to show that you can apply the same thing, not for bulk excitation where you cross 2 laser beams in the middle of a sample, but as we are doing at the surface, the things become a little bit more complicated. Besides longitudinal waves, we also excite shear waves. So these are longitudinal waves and these are shear waves, and if you mix them in a natural way at the surface, you get these Rayleigh waves, surface waves, yeah, as you can see here. The speed of the Rayleigh wave is a bit slower typically than the speed of the shear wave, but the longitudinal wave is also a determining factor. Yeah. So here you see the math that you can use, not so difficult to solve, to find solutions of these wave equations in this configuration. So in a vacuum sample, infinite sample configuration. Yeah. In that case, we make use of potentials, just like you have in gravity. You have gravitational force, but you also have the gravitational potential. You can do the same in acoustics. And the solutions are, as you see here, they are not sinusoidal, they're exponential, but sinusoidal exponential is almost the same, yeah, with or without imaginary number in the exponent. So easy functions to work with. Yeah. The special thing about these surface waves is that there's this boundary between the surface and vacuum or air. Yes, and at the boundary it's free of stress. Yeah, it can move freely. Yeah, and this is a condition that we can use to find particular solutions of the wave equation. Yes. So the important things are stress. Yeah? Hooke's law is important, which couples stress to displacement, and of course the source. Those are important. And okay, then you get some complicated equations, but for which you have to. So in the end, you get a set of equations, as you see here, which contain all these material parameters. Yes. If you have a source, then you have here the source. If you have no source, there's a 0 here. And you have to look for so-called eigenmodes of this equation, which actually means you have to look for zeros of this determinant. When you do that, yeah, you do all of this for sinusoidal solutions. Then you take a Fourier transform, which is giving a kind of mixture of the source. In this case, it's the intensity pattern as a function of frequency and k, the wave number. You mix it with the solution for sinusoidals, and you take the integral, and you can have any solution for any wave shape or temporal shape. Yeah. So here we start from the potentials, then we go to the displacements, and then we go to the final solution in space and time. This is still in frequency and wave number. Yeah. I have a question. Black, yellow, red. What does it remind you of? Okay, I think you know. Yeah. Tonight, 9 o'clock, Belgium, Wales. I will miss it because I'll be on the airplane. Okay. This is how the displacement function, the spectrum of the displacement looks like in frequency. So you see that there's like it's quite boring. It has some feature. This slow feature is actually the thermal part of the solution, and here this kind of wiggle, yeah, corresponds to the acoustic part. This is a damped acoustic wave. So this is before you take the Fourier transform to go from frequency domain or wave number domain to time and space domain. And if you solve it, if you take the Fourier transform, you get these surface waves. There are many kinds of surface waves. You can have it in solids, yeah. And this is what you typically have. The solution that I show in the movie is typically that So the response to heating is a wave, Rayleigh wave, and then and thermal expansion. This is the like a kind of steady state jump, and the thermal expansion in the end is decaying because of thermal diffusion. Yeah. Interesting is that if you look at glassy materials, because as I said we do material research. If you have glassy materials, everything becomes frequency dependent. Speed of sound becomes frequency dependent, becomes also complex. Even the heat capacity becomes frequency dependent, and even the thermal expansion, so the rate of expanding, becomes frequency or time scale dependent. And this is what you see here. This example is calculated for glycerol, and you see that instead of at some temperatures, that the sample doesn't expand immediately when you heat it, but it takes time to expand. So there's even more information, like the time dependence or frequency dependence of the thermal expansion. If you heat up glycerol to be a liquid, then you have this kind of solution here. Yeah. Then you have capillary waves, and then even the gravity comes in, and also surface tension you can determine from that. It's a bit difficult to measure capillary waves because glycerol is transparent, so you need some reflection of light, but it's possible. So and you can calculate this in several configurations. So you can have Rayleigh waves. In this case, it's running at the bottom. You can run at the top. Doesn't matter. You can have leaky Rayleigh waves. So if you couple a solid to a liquid, you see that the waves are radiated into the liquid. This is typically what happens if the solid is faster. If the waves are faster, then they are supersonic. So that's why they radiate here. You can have. There's one Dutch person, at least one in the audience. These are Scholte waves, after the Dutch person here. So those are waves which you excite at the interface between the solid and the liquid. They travel more or less at the speed of sound of the liquid. So they're almost like bulk waves, but they have some spatial penetration. And it depends on the materials how the waves will propagate. Because, for example, these are also Scholte waves. But plexiglass is softer than glass, so that's why these waves are more confined. If you have waves between solid and solid, they are called Stoney waves. And if you have waves in a thin plate, they are called Lamb waves. Lamb waves, you have many kinds. It's a bit difficult to see here, but the top ones are asymmetric. They move like a kind of snake, while the bottom ones are symmetric. They are more difficult to excite because they require like compressing and tensing of the sample. And they travel because of the stiffness, effective stiffness of the sample. They travel at different speeds. Now I will go to a first step towards applications of these surface waves. Yes. So on layered samples. So as I said before, the interesting thing about these surface waves is that they have the penetration depth similar to their wavelength. This is not really a correct drawing, but it shows, I try to show that the penetration depth here at the long wavelength is deeper than the penetration depth at the short wavelength. Yeah? The amplitude actually doesn't matter. It shows that the amplitude is going down with depth. Yeah? And so we use this in our lab mainly to measure coating substrate samples, to characterize coatings or substrates. Typically it's a coating which is very thin, we want to characterize. You can also do it in multi-layer samples, as you can see. This is this sample you have to turn around because okay, whatever. So the penetration depth is proportional to the wavelength, yes, and so you can feel this or you can visualize this by looking at the speed of sound as a function of the frequency or the wavelength, because they are coupled, of course. So, and what you then see is that at low frequencies, the wave is penetrating deeply into the sample, and so and then at some point the coating is actually negligible because the wave is so deep that it forgets about the coating. So then you feel the wave is feeling the speed of sound of the substrate. If you go to higher frequencies and higher frequencies, then the speed of sound is changing. It feels more and more the coating. Yeah. So depending on the frequency or the wavelength, you can determine the two. Both speed of sound, Rayleigh wave. I shouldn't say speed of sound. I should say Rayleigh wave velocity. And where you go from one regime to the other regime depends on the thickness, of course, of the coating and on the elastic properties. This is an example which is a bit more complicated. It's for a 3-layer sample. So you see that there are different features in these in the dispersion curve of the velocity. First of all, you also see that you can have more ways that waves can move. If you make the sample more complicated, you have more ways of motion, which follows from the equations I have shown you. This is here we're trying to show that at different frequencies, you have different distributions of energy in the sample, as you can see, and that's why you are more sensitive to top layer or the middle layer or the bottom substrate. This is an example of plate waves, asymmetric and symmetric, and you see there are several ones, and they are very dispersive. So it means that, for example, here at low frequencies, the speed of sound, the wave speed is small, which means, okay, as you know, I think the speed of a wave is determined by the modulus. The more stiff the sample is, the less compressive, the faster the waves are going, and inversely proportional to the density. Yeah. Now, if you go to a low frequency, it means the wavelength becomes long, and it goes deeper actually than the thickness of the sample. So what the wave is feeling is not only the sample, it's also the air. And air is quite soft compared to solid materials. So that's why if you go to low frequencies, long wavelengths, you more and more feel the soft air and the wave becomes slower. Yeah. If you go to high frequencies, the wave is faster. These other modes here, those correspond to waves which are actually not only going along the surface, but they actually have some also kind of double reflections in the sample. These limiting cases here, these asymptotic values, are related to standing waves across the film instead of running waves along the film. How to measure? Yeah. To measure, we excite waves at one position. This is excitation of a pulse in time and also in space. In space, I mean, we have a thin Gaussian point. Typically, we use lines, laser lines, to excite the waves. So, and then this, and that's what you see here in the bottom left. It's a bit small, but you have a Gaussian wave. When you look at the sample very close, at the displacement of the sample very close to the source, the wave is Gaussian. Yeah. But then when you have these films, these thin films, because the speed of sound of the waves depends on the frequency, yeah, the high frequencies, short wavelengths, they feel only the film. So, and the film is hard, so they go fast. The low frequencies, they go slow. So, and that's why, depending on if you let the wave propagate a bit, that the different frequency components of the signal will propagate at different speeds, so they are dispersive. And that's what you can see here. So these are wave packages measured at different distances from the source, and they are becoming more and more broad. And you see in this case the high frequencies arrive first and the low frequencies arrive later. You can also see it in this kind of graph. So an XT matrix, so this is the signal amplitude as a function of, or the signal displacement can be positive or negative, as a function of space and time. Yeah? And the wave package has some kind of speed, but it's broadening because there are components that travel a bit slower, as you can see here. So it's dispersive. Yeah. This is on the bottom left. You see the theoretical dispersion curve. Yeah. How can you determine it experimentally? By taking, first of all, by taking a Fourier transform of this matrix signal as a function of position and time. You take a Fourier transform which converts time to frequency and x space to wave number. So then you have this wave number and frequency plot. Yes. And as we know in wave theory, the speed of sound equals c equals omega over k. So from omega and k, from these maxima in the energy plot, you can get the speed of sound as a function of frequency or wave number. Yeah. So from that we can determine such a dispersion curves, and from the dispersion curves we can get material properties by doing the math and making fits. Interestingly, okay, this talk is about light and sound, but I still wanted to say that you can also exploit the photothermal effect, because as we have seen, we have also this thermal expansion, and then which is disappearing depending on time, and this decay time is related to the size of the grating, because a big grating takes more time for the heat to diffuse and to remove the grating, while a very narrow, fine grating, it's much faster to remove it by thermal diffusion, and we can exploit this. So if you have a long grating, the long grating, when the heat is diffusing, it penetrates to the left and to the right, but also from top to bottom, and it feels the substrate. If you have a fine grating, it doesn't. It only feels when this grating is disappearing, it only feels the coating. So that's why you can also use the decay of the thermal expansion by thermal diffusion to measure or to determine the thermal diffusion as a function of depth. So you can do depth profiling, not only acoustic, but also thermal. Now to the detection, because I said how that if we can detect waves, we can extract properties. How do we detect waves? First, some numbers, too many to read. I will not read them. But just some numbers that give some idea of typical values. Changes of temperature. Yesterday we have seen in the talk of Paul Beard that in biomedical applications, the temperature rise that you get by shining light, pulsed laser light, quite powerful lasers, with energies of about some tens of millijoules, that the temperature rise is smaller than, but maybe of the order of kelvins. So, and that's what you can have indeed. When we do material science, we don't have to be so careful. So we can typically have not less than a Kelvin, but tens of Kelvin, and even much more. It depends on the pulse energy. Okay, typically millijoules, until 100 millijoules maybe. But it mainly depends on how much you focus the laser beam, and also how much the laser is confined, not only laterally but also in the depth. So then you can have actually locally and on very short time scales you have thousands of kelvins. And that's why you can use laser ablation. You can actually evaporate the material at the very top surface, and then this impulsive, or let's say conservation of impulse, will make that you also excite waves. But you can also do it more softly, just thermal expansion, which is also giving stress and which is making waves. In any case, temperature variations between millikelvin, if you are poor, you don't have expensive, powerful lasers, and thousands of kelvins. If you then take the thermal expansion coefficient, which for solids is of the order of 10 minus 5 per Kelvin, so 1 Kelvin gives you a compression or actually expansion of 10 minus 5, but some liquids have 10 minus 4, even 10 minus 3 if you choose the liquid properly. So if you combine that, then you can generate laser-induced strains, expansions of the order of between 10 minus 8 and 10 minus 3. 10 minus 3 is already quite a lot. It means you are starting to be non-linear in the wave propagation. To be linear in the wave propagation, typically the stress should be smaller than 10 minus 4 or 10 minus 5. If you have, yes?
How do you link the amplitude of the strain to the change in the refractive index in a liquid?
Yes, there's another law for that. For example, there's Clausius-Mozotti, which tells you that the refractive index is proportional to the density. The more molecules you have, the more light will slow down, because it's slowing down because of molecules. So, roughly speaking, I'm setting them equal. If you have, but of course it's not exactly true, because you also have the polarizability that plays. But roughly speaking, a change of 1% in density gives you order of magnitude 1% in the refractive index. Okay. Do you agree? Because you know better than me, actually.
No, I would have expected it to be smaller in the liquid than in the solid.
Okay, maybe, but let's say order of magnitude is and it depends on the optoelastic coefficients. Yes, but yeah, but okay, this is rough. Yeah, that's why you have these big ranges of values there. Now, if you we measure typically. We can. It's actually good that you asked the question, because when you want to measure waves, I always speak about displacement, but you can also measure the change of refractive index. because refractive index is also changing the optical path length, and you can really exploit that. And I will show some examples. But so if I go back to now to displacements, for example, if you have a thermally induced expansion of 10⁻3, yeah, and you have this over 1 millimeter, so the wave is penetrating, or the thermal expansion is penetrating over 1 millimeter, then the displacement is 10⁻3 times 1 millimeter. So it's 1 micrometer. So that's how you can estimate the displacements. Yeah. And when you do that, then you arrive at displacements for typical lasers, pulse lasers, modulated CW lasers, yeah, rather powerful. You arrive at displacements and also you have to speak about frequency, because the longer you heat, of course, the bigger the displacement. Then you arrive at displacements of 0.5 picometers, so 10⁻12, 10⁻13 picometers. So those are small and also difficult to measure, until nanometers and even micrometers. But for micrometers, you need low frequencies. So those are that's the order of magnitude of displacements that, if you want to detect the waves, you have to measure them. You don't only have to be fast, you also have to be sensitive. Yeah. In the bottom here, you see how you can make these estimates. For example, if you want to estimate the temperature change, you need the heat source, delta Q, heat capacity, density, and the volume. So that's why the volume of light is important for these kind of things. Somewhere here, here it is, in the bottom, there's the Grüneisen parameter, which was also mentioned yesterday in the talk of Paul Beard. So that's a kind of coupled parameter that gives you a kind of overall efficiency of converting light into stress. Because you can also measure stress, yeah? The force which is excited or which is going along with the wave propagation. Yeah. Okay. Here's an example of an optical setup. I will go in more detail later. Yeah, but again, you see those signals with a expansion, then acoustic waves. They are damped in the end, and then you have thermal diffusion. Yeah, and from this technique, transient grating excitation and heterodyne diffraction detection, you can get absolute numbers. Yes, and so here you see that the displacement were of the order of 30 picometer per pulse energy of 50 microjoules. Yeah. And 50 microjoules is a rather typical amount of energy that you have with a pulse laser. I should say with a picosecond pulse laser. No, sorry, this is more like for a femtosecond pulse laser. For picosecond, we typically have millijoules, 1 millijoule, yeah, at maximum of energy. The challenge, another challenge besides being able to measure small displacements, is to measure rough samples, yeah, or all kinds of samples. And actually, so we are not, our lab is not a material science lab. Sorry, it's a material science lab, but we don't make materials. We always have to beg somebody to give us a sample, or people come by themselves and bring us samples and ask us to characterize. And the samples can be very different. For example, this is a silicon wafer. Free surfaces of liquids to measure capillary waves to get information about surface tension. Components that are used in this is from a helicopter here. Yeah, this is the slat rack. It's from an airplane to bring the wing out. This is a bit magnified. This is nanocrystalline diamond, yeah, very thin layer, 800 nanometers. This is a sample, a protected steel fuel cladding from a nuclear power station. So you see it's very rough, yeah, but people want to know the elastic properties because they say something about the quality of the sample. The stiffness of the sample depends on the structure, so it's a useful quality, and also the thermal diffusivity depends on the structure. So they are useful things to measure. This is there's a needle here, but this is not laser excitation. But anyway, this is a foam. Yeah, if you want to determine the elastic properties of a foam, you have to really look very locally and excite very locally, and then look at the wave propagation along this. So you can imagine that it's quite complicated. Yeah. Another complication, as we have seen in many previous talks, is that light is diffusing in some samples, so that makes it more complicated. Composite plate cracks. This is a polymer sample. I will show the example later. So there are many kinds of samples that you can investigate, and every sample will need a dedicated solution. And that is why in the following I will discuss several techniques to measure wave displacements, and all of them are useful in particular cases. Yeah. So now I go to detection schemes. Here is an overview of I think all of the schemes that are discussed further in the talk. The main distinguish or the main separation here is between optical, yeah, and piezoelectric, because I was like maybe insinuating that you need optical techniques to detect small displacement, but actually piezoelectric is even better, provided that the displacements are not, well, piezoelectric can be fast, it can be gigahertz, yeah, but you need contact with the sample, and that's sometimes a limitation, or often a limitation, but it's a very good technique. Optical techniques with their advantages and disadvantages. Okay, we will see. So the piezoelectric effect is okay. I will not go into the physics of it, but it's based on converting stress to polarization, change of polarization, and then convert it to a change of voltage over a sample. Here's again some estimate. Yeah. I estimated, I don't know, I just put some rough numbers again, that for example if you have typical strains in biomedical applications, yeah, with a typical piezoelectric transducer and the piezoelectric transducer, the piezoelectric coefficients is given here, so I just took it from some supplier. If you put those numbers there, so you put the strain, you put the piezoelectric coefficient, you put the thickness of the sample, and okay, that's it. Then you arrive at some millivolts of signals for typical strains. And okay, in electronics to measure millivolt is not so big of a challenge. I think you can measure till microvolts. So it means even for small strains you have quite some signal. So that's why piezos are used in biomedical applications, biomedical photoacoustics, because the stresses are small. You cannot heat the sample too much, I mean the body too much. So that's why you need a sensitive technique. Yeah. And we have seen the application of photoacoustic imaging, yeah, in which you can use, for example, phase array detection to steer the sound in different directions, which I'm very fascinated about, but this is not my talk, so I will skip this slide and I will not go further into it. And it was explained very well in previous talks. A technique that you can use to measure surface displacements, so for this to measure these Rayleigh waves, is laser beam deflection. I put it as a first because it's very simple to set up, and it's very sensitive and very useful. It works mainly, okay, first let me show how it works. So you have a wave which is passing by, you focus a probe beam to the sample, yeah. The probe beam size, the spot size, should be smaller than the wave, otherwise you don't measure a particular point of the wave, you measure it completely, so it has to be smaller. Yeah. You reflect the beam, yeah. You collect it with the lens. This laser beam was focused, so this one was diverging, so after the lens it's again collimated. You split the light beam in two. You have to make it big enough that it's big enough compared to your mirrors. So the two mirrors, one is behind each other, as you can see here. Split the light in two, and you send the light, one part of the light you send to detector 1, the other one to detector 2, and you look at the difference. Yeah. Now what happens is that okay, this is before the wave is passing. You balance the light, that the amount of light reflected by the green mirror is the same as the one by the red mirror. So the difference between the two detectors is 0. So you start from a 0 signal before you do the experiment. You can do this by putting this on a tilt stage here, and by playing a bit on a translation stage and a tilt stage. So then the wave is moving. Yeah. So now the sample is a bit sloped. So that's why the beam is deflecting. And when the beam is deflecting, the balance here of the light on the green and red mirror is changed. So you will have a different signal on the detector. Yeah, a bit further. Yeah, a bit further. So the beam is moving, and the light balance is changing as the wave is passing. Yeah. Interesting is it's an advantage and a disadvantage is that the wave package here was a Gaussian, which is typical for Rayleigh waves. By the way, it's maybe strange, but actually when you excite a surface wave with light, you would think that there's a bump moving from the left to the right. Actually, it's not true. It's a dip which is moving. What is happening is that you have a thermal expansion. That is a bump, but the wave, the acoustic wave, is a dip that's moving away. Okay, here it's shown a bit wrongly. So actually, it's a dip instead of a bump. In any case, the bump is Gaussian. In this case, it was excited, for example, by focusing the light to with a cylindrical lens to a line. But the signal is bipolar because it's the slope, it's the spatial derivative of the wave. And that means also that this technique is more sensitive for short wavelengths or sharp waves than for smooth waves. Yeah. Or if you convert to time, it's more sensitive for high frequencies than for low frequencies. It's a high pass filter response. Yeah. So it's not so suitable for slow phenomenon and long wave packages. Sometimes, okay, can you use the beam on this technique on rough samples? The answer is yes, if you modify it a bit. The people in Nottingham, some people here in the audience from Nottingham, they developed a technique where they use array of detectors. So you have an array of detectors, and so if you have a speckled beam, and we know everything about speckles now since from yesterday. If you have a speckled beam, then all these speckles will move depending on the beam deflection. Yeah. But if you have all these detectors, then you can look actually at every edge, how every edge is moving. And so instead of taking the integral of everything, which would give you nothing, because if you have a speckle pattern moving, you take the average, nothing will happen. But if you look at the individual edges, you can actually detect every change. And if you then sum up all these changes, you have one global change. And you have a beam deflection detector that works also for speckle patterns, so for rough samples, which is quite nice. Another technique that also was already mentioned in several talks, but I'm repeating it because it's the basis of all the techniques that are discussed later, is the Michelson interferometer. So we know that the basis is that we cross two laser beams, one which has gone to the sample and the other one which has gone to a mirror. Yeah. And we use a beam splitter to cross them and to mix them again here on the photodetector. Yeah. When the sample is moving, then the optical path of the sample beam, probe beam, is changed. So the optical phase difference with the other beam is changed. And in the graph here, you see what happens if you change the optical phase or the distance of one of the beams. What happens with the intensity of the interference pattern, which you can see here in green? Yeah. Well, it will move because you will go from, for example, from dark to light, or from a little bit light to more light, or from light to dark, depending on where you have started. Yeah. So that's in a Michelson interferometer, and also in all the other interferometers. If you want to detect small displacements, you want to put yourself here on a big slope, such that if the sample moves to the right, or if the optical phase change is increasing, you have an increase of intensity, and if it's decreasing, you have a decrease of intensity. So that's a good point to put yourself. If you have bad luck and your interferometer is sitting here on the top, if you move to the right, the signal goes down. If you move to the left, the signal is also going down, which is not what you want. You want a monotonic relation between the displacement and the intensity. So that's why you need some control of the statical optical path of the interferometer. And this control, for example, can be done by putting this reference mirror on a piezoelectric mirror that you can move to stabilize the interferometer, or it can be done by putting, for example, a Pockle cell or a liquid crystal that changes the optical path, and with a feedback system that you can control where you start. Yeah.
What is the amplitude of the interference that you get?
Okay, as we can see here, the optical phase difference is given by 2 pi, which is the optical phase difference that you get for one wavelength, lambda, and C here is the displacement. So if you have a displacement of, let's say, more or less a quarter of a wavelength in this direction, you have you go from completely light, dark to light, or light to dark. So more or less for lambda over 4 displacement, you get a full change of intensity, at least provided that the light of the mirror is equally strong as the light from the sample. I don't know if
how do you compensate the temperature and other vibration?
so the temperature and the vibration you can compensate by, well, you have to we have to make
Any
use
external influence.
yes, external influences. Sometimes you cannot compensate. For example, if you want to measure slow displacements of the sample, they are as slow as all the other changes and you cannot distinguish. So you don't know what is changing. But typically in laser ultrasonics, you are using megahertz or kilohertz or even gigahertz. So that's very fast. So, and it means you're not interested in these slow changes and you can actually remove them. And how do you remove them? By having this feedback system where you put this focal cell or mirror. So for example, if the interference pattern is going to the right, your electronics is pushing it back to the left by moving. Yeah? Or the focal cell will change refractive index and you can stabilize. And you only stabilize for the low frequencies, which are not your signal. You don't stabilize for the high frequencies, which are your signal. Yeah? So you need a stabilization system. And also nice about these interferometers is that you can, by pushing your interferometer to the dark and to the light completely, and by measuring the voltage that you have from your detector signal, you know the top and the bottom, and from this, with this simple formula here, which is just a derivative of this function, you can actually calibrate the interferometer. Because you know, as I said, roughly lambda over 4, but there's some pi factor, lambda over pi. Yeah, lambda over pi corresponds to light going from light to dark. Yeah. You have to know the optical wavelength, but you know where you have bought the laser, so you know it. So
but you need to stabilize the interferometer, correct?
But yes,
to be in the middle of the.
Yes. You need to stabilize it, and sometimes it's a challenge to stabilize it. It's not a microson interferometer, but it's very similar. Maybe let me show first the top one. This is a very cheap interferometer to make. Well, the other one was also cheap. I mean, beam splitter and mirrors, it's cheap. But this one also. And this one is more stable. Okay, how does it work? Instead of using a beam splitter, you use a diffraction grating to split the light into different diffraction orders. And you can also buy the grating such that you mainly have +1 and -1 diffraction, and not so much of 0 order diffraction and plus or -2 and so on. Yeah. So it means you need a sinusoidal grating, but those are available, or you can even make them yourself. So then you have the two beams, which are the ones that are going to interfere. One is going, in this case, through the sample. So this is for transparent samples, where you want to measure, for example, the change of refractive index. And one is going through, okay, if you are rich, you can send it through a focal cell. If you don't, then you just send it through nothing. So you can put a focal cell here. And so now the two beams have collected information about the sample and about the focal cell. Focal cell with which you can control the optical path. Then you want to cross the laser beams again to make an interference pattern. So how do you do that? Well, first of all, you cross the two laser beams here in this place, and well, you could maybe put the detector here, but you don't do that. You put here another phase mask, another grating, which again is diffracting this laser beam with +1, -1, and so on. And one component of the diffracted light is going in the horizontal direction. The other beam is also diffracted because of the grating. It goes in this direction and this direction. But one component is going in the horizontal direction. So, but in this way, you have lost some light, because you lose some light in the other diffractions. Also here, you lose some light. But there are two components of the light beams that are together and give you an interference pattern. So you have made a microson interferometer, but you have split and joined the light in two different places and in a different way. But it's still an interferometer. And it works in exactly the same way as the other one. The advantage of it is that in this case, when your laser table is shaking, you easily have changes of the interference pattern, because this mirror will shake differently than that sample. Than the sample here. yeah, because of the configuration. But in this case, for example, when this lens is moving, because of vibrations, environment, it will move more or less in the same way for this beam and that beam, same for all the other things. So it's a more stable interferometer. Yeah, and yeah, so it's quite handy to use this configuration. You can do the same in reflection mode, because if you want to measure displacement because of, for example, because of surface waves, then you can again separate the two beams here. You have the lens here, then the sample, one beam is going to the sample and the other beam is also going to the sample. That's a bit weird, but as long as the phenomenon that you want to investigate is happening here and not here, you can actually use one as a reference and one as a sample. Yeah. So that's what you do, and because the sample is now reflecting, the beams are reflected back. They are again mixed, yeah, here. And how to separate them then? Well, you have to use a lambda/4 plate, which is playing around with the polarization. You go from circular to linear. From linear to circular. When you come back, you go from circular to linear, with a polarization change of 90 degrees. So that's why the beams that are coming back are not going back to your laser, but they are going to the photodetector. So so in this way, again, you are mixing the two beams. You have an interferometer, and you are measuring. You are looking at the difference in displacement in optical path between this point and that point, and you can use it for detecting waves. For example, if you detect a wave in the middle, well, maybe not exactly in the middle. It will first arrive at detection location 1, and a bit later it will arrive at detection location 2. So you see the wave two times, once negative and once positive, because once it's pushing forward probe beam number 1, and the other time it's pushing forward probe beam number 2. So again, very simple interferometer. And in principle, it can work for everything. Nevertheless, people are also using other types of interferometers. Sorry. For example, this one, the Sagnac.
Just one question.
Yes.
Have you tried to use the chirographic interferometer in your experiment?
Sorry, which one?
A chirographic interferometer.
It's in one of the next slides. Yes. Yeah. Because of rough samples. Yeah. Sagnac, because this talk is in France, so I try to use as much French scientists as possible. It was not difficult. I mean, most of them are.
But in Belgium, you speak French or English?
English. When we speak to our French compatriots, we speak English. Okay. Now, and so do they. Yeah.
But you can speak Spanish if you want.
Mais je peux parler français si vous voulez.
Oh, espagnol.
Or Spanish, yeah, why not, huh? Because now, yeah, okay. This is recorded, so I won't. Yeah. So the Sagnac interferometer, it's an interferometer, so you are mixing two light beams. But in this case, it's the two light beams have seen even the same position of the sample, but at a different time. So, how do you do that? The light beam is split. It's in two, and one part is going to the sample along the shortest road, straight ahead. The other beam has to make some additional path, and so it will arrive a little bit later. Okay, light is going fast. It's going how much? 3 nanoseconds. 1 meter is 3 nanoseconds. Isn't it? Yeah, so you need quite some space to give it some delay. But so it will arrive at the sample a little bit later. Yeah. Then when the two beams are going back, the one that has taken the long path, because of its polarization, it will on the way back it will take the short road, and the one that has taken the short road on the way there, it will take the long road on the way back. So actually, in total, they have taken the same road, but in a different order, and they will arrive at the detector at the same time. So they will interfere. They have to arrive at the same time, otherwise they would not interfere. They would be separated in time, and one would arrive, the other one would arrive, but no way to interfere. But here they do, yeah, because of the symmetry of the setup, yeah. So normally what you would expect, okay, they have seen the sample together, well, they have seen the same sample, so the interference will always be constructive because they use the same path. If there's no path difference, then they see the same. Except if between the arrival of the first one and the arrival of the second one, the sample has moved, then one will have put a little bit more or less time than the other one. So and that's the principle. You are looking at the fast movement of the sample, so you're actually converting the speed of the sample into a change of optical path, yeah? Which is different from the previous case where you were looking at the displacement of the sample that you converted into a change of interference intensity. So this one, and you can play with the delay by moving these two mirrors here. If you move them top to the top, then the second beam will arrive later. If you move to the bottom, then the second beam will arrive earlier. And so, but you measure the velocity, so the response is a kind of high pass filter, yeah. So you can tune the delay to measure very fast waves or slower waves. So for slower waves, it's better to put the delay a bit longer, because then there's more optical path difference between the two. It's again, because of the symmetry of the configuration, it's a stable interferometer. It needs no stabilization, because the phenomenon is, well, no, maybe you need some stabilization because you still want to set the interference pattern on the good slope, but I think that can be done by just tweaking some of these mirrors here. Without very special things. In the article that describes very nicely the technique, one of the articles, this was technique is often used in the lab of Oliver Wright or Samu Matsuda in Japan. In the same article, which is given here, they also give a nice optical setup, like to scan the probe, because usually scanning the probe is not so easy, because the alignment is changing. But in this setup, they scan the probe and keep the pump, or the pump doesn't matter, by just rotating this mirror here. And interesting is that in this configuration, in this optical configuration, the probe beam that is coming back is following exactly the same path here, even if you rotate the mirror, yeah? Which is nice, symmetric. Sometimes you are rotating the mirror, but the probe beam is moving its position and you cannot track it anymore. But in this configuration it works. So I can recommend this article for that. A configuration which was in a recent article by the group, okay, I forgot to put the reference here, but it's the group of Bordeaux, of Bertrand Audouin and Clément Rossignol and so on, and where some of the speakers here are coming from. So there this is a kind of Sagnac interferometer, but where they, instead of sending the beam to another path, they use the fact that they send the beam, or they split the beams, but they have a birefringent crystal, and so one beam, its optical path length is different because it's polarized differently, and the speed of sound is different depending on the polarization. So it's a more compact setup, and you are using the optical anisotropy actually to play with the delay. You cannot tune the delay anymore because the refractive index anisotropy is fixed and the thickness of the crystal is fixed, but it's nice because it's so compact.
I have a question.
Yeah.
Why you are not using Fabry Pro interferometer?
It's one of the next slides.
I apologize.
Thank you. Sorry. Okay, why don't we use the laser Doppler vibrometer first? So the laser Doppler vibrometer, because so many people are using it in non-destructive testing. So it's a commercial device. You just push the button and it works. Contrary to the interferometers that we make ourselves, it's not only pushing a button typically. But okay, they are not so bad. So laser Doppler vibrometry. The principle is that when we want to detect waves, when the wave is moving, it has a velocity. When light is reflected from a moving object, reflected from the sample, it will change you'll have the Doppler effect, yeah, as is shown here in the animation of one of the producers. So the Doppler effect changes the frequency according to this equation. Yeah? Omega 0 is the starting frequency. The second one I will explain a bit later. But so the Doppler effect is just simply proportional to the ratio between the speed, the velocity of the object divided by the velocity, the speed of light. So very simple. Now, how to detect these changes in frequency of the light? Again, it's a kind of microson interferometer. But now you are mixing the light which is going to the sample by a reference beam, which is staying inside of the interferometer. And you are doing something in addition, so it's not an ordinary microson interferometer. You are shifting a bit the frequency of the reference beam or the sample beam, doesn't matter. So one of them you are shifting in frequency with an acousto-optic modulator, because it's fast, but you could also use a Pockle cell or other techniques, which is written here as a Bragg cell. Yeah? That's actually what people call optoacoustic effect, the optoacoustic modulator. So where you are actually using sound to change light. In photoacoustics we use light to produce sound, so it's not it's different. Yeah. I will not explain how it works, but nevertheless it's interesting. Yeah. Now, so we have, it's an interferometer because the frequency modulated light that is coming back from the sample is mixed with the light, the reference light. If the frequency is of light, you have one laser beam, and the other beam, if they are the same frequency, they will have a steady state interference pattern. If for the other one the frequency is changing, it will convert, this frequency change is like kind of converting into a phase change, and so you'll have a change of interference pattern. So you'll have a beating. You'll have a beating frequency between the frequency of the reference beam and the frequency of the sample beam. And this beating frequency is equal to the Doppler frequency. Yeah? It's a frequency difference which is induced by the motion of the sample, which is actually coming out as the interferent, as the frequency at which the light of the mixed beams is beating. So then this beating frequency or the Doppler frequency is proportional to the velocity of the sample, so it's changing in time. So it means if you want to determine the velocity, which is the quantity of interest here, you have to measure the frequency as a function of time. To do that, people are using a phase-locked loop, which is actually an electronic oscillator which tries to follow the frequency of the electronic signal. And so it just consists of a multiplier, low-pass filter, integrator. So it's quite simple, and so it tracks the frequency. In this way, you are tracking the velocity of the sample. If you buy such an instrument, you can, and you pay enough money, you can choose between measuring the velocity, which is done simply with a phase-locked loop, or measuring the displacement, which is actually taking some kind of difference error signal from this. So everything else than this velocity change, you are trying to measure. The velocity changes you can measure typically until 20 or 100 kilohertz. The displacements is everything which is faster, because it's the error signal of the previous one. So that can go typically in the past until 20 megahertz. I think nowadays you can buy them until gigahertz. So it's a quite efficient device. One of the nice things is that even scattered light will have the same change of frequency. So it's enough to have a signal. You don't need a nice beam. So there are actually only advantages, I think. It's also very linear, very sensitive, yeah, but it's usually not so cheap. So the other things are with the 2 mirrors was cheaper. Okay, this is some theory. Actually, it's the theory of a microson interferometer with a moving sample. So where you see that if you have a change of Doppler frequency of the sample, it's converting into a change of intensity of the interference pattern. Why do we use the acousto-optic modulator? Because if the sample is going forward, the frequency is going up. If it's going backward, it's going down. If you would measure that frequency, you would have positive and negative frequencies, which is a bit tricky because usually, I mean, they have the same effect. Yeah. sine omega t or sine min omega t, it will look the same. If you want to distinguish, what you do is you add to this, you add the acousto-optic modulator frequency, for example 40 megahertz, and then if the sample moves forward, you will go from 40 to 41. If the sample moves backward, you go from 40 to 39. And so you can measure around that, and you can distinguish between positive and negative frequencies. So you can distinguish between the sample going forward or backward, which is useful. Here's a mistake in the title, because this is not laser Doppler vibrometer. You know which one this is? It's French.
Fabry-Perot.
Fabry-Perot. This is the Fabry-Perot.
Fabry-Perot.
Yeah.
There are two guys, no more.
Yeah, yesterday we looked it up on Google. Indeed, so Mr. Fabry and Mr. Perot, both French. So it's also an interferometer which is very handy and okay for rough samples, because it's also based on the Doppler effect. It only needs the frequency, the color of the light, to have information. Is it cheap? We have to ask Misha, because you can make it yourself, but you can also buy it. What you mainly need is two highly reflecting mirrors, which are very parallel to each other, or you need some kind of cavity with mirrors. Yeah. The principle is, so you want to detect changes of frequency, but in optics frequency and wavelength are mixed. So, and how you do it, you make a standing wave of light in the cavity, and the standing wave will be, let's say, constructive. It will happen if the wavelength of the light is fitting exactly in the cavity. If it does not, the standing wave will not be very well excited, and that's why here you see that as a function of the wavelength of the light, which is converted to something else here, as a function of the wavelength of the light, you will have like these peaks in the transmission, very sharp peaks. If you have many round strips, so it means if the mirrors are highly reflective, you have a very sharp condition for the wavelength, and you have sharp peaks in the transmission. So the transmission of light, which you can measure here in the backside with the detector, as a function of the wavelength of the light, yeah, or the frequency. So now, if the sample is moving, the frequency will be modulated, and the transmission, if you, for example, if you put yourself here on the slope of one of these peaks, the transmission will go higher and lower monotonically, yeah, if you do it well, monotonically with displacement. Yeah. If you put yourself at the top of the peak, it will not be monotonic, so that's not so useful. Yeah. Maybe one of the disadvantages is that you have to put yourself on such a sharp peak, so you need a quite precise control of the distance between those mirrors to be on a good position. And typically, at least in our lab, we were using a feedback system to keep on that peak, to stay on that peak, to have always the same slope. But the slope is very high, which makes that you are very sensitive to small changes of velocity. So it's a very sensitive interferometer. And, as I said, robust in terms of scattering samples, because you only need some light to go back and forth, use some speckles, and it's enough. Yeah. One disadvantage is that because the light needs some time to interfere with itself, during that time, if the sample changes, it will be, let's say, the interferometer will be confused. So, let's say the characteristic response time of this interferometer is more or less given by the time needed for all these round trips. So if you have very high reflective mirrors, in order to have a very high sensitivity, then you need, then you will have a quite slow response. Well, slow, hundreds of megahertz, not gigahertz. Yeah.
So sensitivity is the finesse.
Yes.
French name.
Yeah.
Why you are not using confocal Fabry-Perot?
Because in PowerPoint it was easier to draw this line. But of course you can have confocal Fabry-Perot to have, which is I don't know. Maybe I don't know how much better it is. I can imagine.
Well, the thing is that in terms of alignment, if you have plane waves. It can be
you have kind of automatic alignment without this problem of the.
And there's another French guy, which is Pierre Cohn, Institut d'Optique, created
created the,
confocal.
okay. So,
It's much better for alignment, because otherwise you see the light and
yeah,
it's difficult to align the two plane mirror.
yeah.
Pierre
it's
Con,
gone.
French guy.
Okay, again, French. Yeah.
C'est la vie.
C'est la vie. So, and you can use it in you can put a detector here, but of course what does not transmit is reflecting, and you have the similar sensitivity on the reflected side, depending on what is more convenient for your application. But so indeed confocal is most commercial ones are confocal because of this advantage. Yeah, so I took an example here of the bandwidth, like 300 megahertz for a Fabry-Perot of 10 millimeters, and with a finesse of 100, roughly. A bit different topic now. I always speak about displacements, but displacement is going along with stress, because it's the stress which is driving the displacement, and the other way around. And if you have acoustic waves, so they always have stress, and this stress is changing a bit the refractive index. Yeah, actually also again via the density and the polarizability. But so they change. The stress is changing the refractive index of the sample, and you can exploit this because the optical reflection coefficient of a sample is given by this equation here. Depends on the refractive index. This is for perpendicular incidence and for a sample in vacuum. So if you have a change of refractive index due to the stress, you will have a little bit of change of the reflectivity. As I said before, the typical changes of refractive index of stress and refractive strain and refractive index are of the order of 10 minus 6, yeah, so quite small, but, and the reflectivity also, change of reflectivity, 10 minus 6, but it can be detected. Yeah? If you have a good system, these small changes of reflected intensity of the light can be detected. This slide is about this, but it's about something in addition. It's about how to use an optical delay line to measure very fast changes of optical reflection. So the principle is as follows. You need one laser only, one pulsed laser, which you are using to generate the light to use to excite the sample, and another part of the light, the probe, you are using to detect the changes of reflectivity of the sample. The reflected light you measure with the photo detector. So the light is split in two. Yeah. So what happens is that the pump light is coming first to the sample. Why it's first? Because the path is a bit shorter. It arrives a bit earlier than the probe light. It's making the change. It's exciting the wave or it's heating the sample, and this is inducing the change of reflectivity, which is not instantaneous and which also takes some time because the acoustic waves, they need time to propagate. The thermal diffusion needs time to disappear. So it's normal that the probe is arriving a bit later to follow the evolution of the acoustic waves and the thermal expansion. So, but since the pump is pulsed, okay, you have this impulsive phenomenon which starts, but the probe is also pulsed because it's coming from the same laser. The probe is only feeling the reflectivity at one instant in time, at one instant in delayed time. So, and for example, if the probe would be arriving before the pump, you would have no change of reflectivity. If it arrives after the pump, you will have a small change of reflectivity. Now, by moving this mirror here, which is in the path of the probe, you can play with the arrival time of the probe. So you can play with the delay time. So you can measure for one position of the mirror, you measure the reflectivity, for example, 1 nanosecond after the pump, then you move the mirror. You measure it 2 nanoseconds after the pump, you move the mirror, and so on. And in practice, you put the mirror on a translation stage, and you measure time, delay time by delay time, how the reflectivity is changing. However, this change of reflectivity is really small, yeah? 10 minus 6. So, and a change of 10 minus 6 of a laser intensity, it's almost impossible to measure because the laser intensity by itself is fluctuating. Even for good quality lasers, there are always some fluctuations of the intensity. So you need to do something more. First of all, you can do averaging. You can measure many probe pulses always at the same delay time after the pump. That's one thing you can do. But still, it's complicated because you have for example, you have some amount of reflectivity, and only 1/1,000,000th of that, 10⁻⁶ typically, is changing. So you have a big amount of light, and only a small part is changing. Yeah? To measure that, you typically make use of a lock-in detector, which is kind of removing the steady state part of the sample and only looking at the small changes, provided that these small changes are synchronized with something, with a reference signal. What is the reference signal? It's the chopper that you put in the pump beam. With a chopper, rotating disc with slits, you are switching, or an acousto-optic modulator. With a chopper, you are switching the probe beam on and off. Sorry, the pump beam on and off. So when the pump beam is on, the modulation, the reflection coefficient will have changed. When it's off, it's not changed. So the light intensity will be, for example, not changed, changed, not changed, changed, with a fraction of 10⁻⁶. So this drawing is completely exaggerated. This change here is only 10⁻⁶ of the total. But a lock-in detector is able to find this periodicity, chopper, pump beam on, pump beam off, pump beam on, pump beam off, because you know exactly at which rate you are doing it, and you give this information to the lock-in amplifier by some multiplications and filtering. It can take out of the signal this modulation, and this modulation is proportional to the change of reflectivity. So optical delay lines, especially in this technique, are used always in combination with a chopper and a lock-in amplifier. So used in all the labs that are using femtosecond lasers, picosecond lasers, it's very common to do that technique. Recently, in the past 5 years, I think, or 10 years, people, although in most labs the amount of money is going down, but on the other hand the prices of lasers are going down as well. So some people are now able to buy these coupled lasers, for example 2 femtosecond lasers, of which the frequency can be the repetition frequency. So the amount of pulses per second, which is typically 80 megahertz for many kinds, for titanium sapphire lasers typically. So or 76 in this case. So the repetition frequency can be completely controlled, and so one laser can be used as a pump and the other one as a probe. And for example, if you put the frequencies exactly the same, then the pump will always arrive at the same time after the probe. But if you put the frequency slightly different, then there will be kind of beating, and the probe will, at the first pulse, it will arrive at this time. A bit later, because of the slight change in frequency, it will arrive a bit later, a bit longer after the pump. And so you are spontaneously modulating the pump-probe delay time, and you can exploit this in your signal averaging process. And it's a very natural way, or a very easy way, to make these graphs here, where you are modifying constantly, you are modifying the time between the pump and the probe. So in this case, you are doing it by exploiting the beating between the two laser frequencies. Yeah.
So these are kind of heterodyne interferometer or something similar?
Kind of, yes, because you are using two interferometers and the beating. Yes.
So what I'm saying is that sometimes, especially in our group, we have practiced heterodyne and homodyne in terms of compensate the vibrations, and you get a very good results. You combine both. Anyway, we can talk after.
Yeah. If you want to know more about these two configurations, there are three labs that I know of that are using this system. It's in Bordeaux, University of Bordeaux, University of Hokkaido in Sapporo, and the lab of Thomas de Corsi in
Constance?
Yeah.
I think Benaperra also.
And Benaperra maybe also, yeah.
Also in the University of Nottingham.
And Nottingham also?
Yeah.
So people are becoming, only in Belgium we don't have money to buy this. Now, an interesting thing about this modulated optical reflection technique, because it's used quite commonly, is that sometimes the sample consists of a transparent layer on top of a reflecting and absorbing layer. So for example, in this case, the sample is dark, so it will be heated by the pump laser beam. It will excite waves going into the sample, but also going into this transparent medium. And the probe beam is going through the transparent layer here, back and forth. In principle, what you would expect is that you measure the changes of reflectivity of the sample, and then you use this optical delay line to detect it. However, you can have something more. This acoustic wave, which is propagating inside of this transparent medium, it will, so it's excited here, it will change locally, because it's a short wave package, it will change locally the refractive index. And if you change the refractive index, as we know from Snell's law, we are in France, I should say Snell Descartes, by that we know that if you have change of refractive index, you have reflectivity change, and so a bit of light will reflect from this kind of moving mirror, moving acoustic mirror. So, and that light will interfere with the light which is reflected from the sample and maybe also from the front side of this. So you have an additional interference effect. You not only have the modulated optical reflectance, but also a kind of interferometer. And if this if this mirror is moving, then the optical path difference between the mirror and the static reflectors will change. So if this mirror is moving, if the acoustic wave is moving, you will have some change of interference pattern. And because depending on how much it is moving and how much is the optical wavelength and so on, this will give interference pattern going on and off. And this is called, this kind of oscillation is called, again French, Brillouin oscillations. Yeah? So this is a kind of, how to say, coherence Brillouin scattering, yeah, induced by your own laser pulse. Yeah? Besides the spontaneous Brillouin scattering that can also happen due to spontaneous changes of refractive index, due to spontaneous acoustic phonons in the sample. There are some equations here from which allow you to convert the frequency of the oscillation to the speed of sound, the speed of the mirror, which is useful. One disadvantage, or let's say one complication, is that you have to know the refractive index, because the speed of light depends on the refractive index. So you need to do some additional measurement to get it. Okay. Until now, I've always been speaking about laser pulses, so always a Dirac function in time, and in space, typically a line source or just plain wave. Now I will go to, again, back to what I said in the beginning. You can also cross laser beams to have periodical, spatially periodical heating. So you have like a crossed laser beams of periodical heating pattern here, which will make these periodical acoustic waves and also a periodical thermal expansion pattern with the advantages that I have mentioned. Yeah. So for example, one advantage is that if you cross the laser beams with a big angle, then you have a narrow or let's say a very fine interference pattern. Yeah. You excite acoustic waves at particular this wavelength, so at this one frequency, and you can, by measuring the speed or by measuring the frequency, you can get the speed of sound for that frequency. If you cross the laser beams under a small angle, here, then the wavelength is longer, the frequency is lower, and you will measure another point on the dispersion curve. This, for example, is the dispersion curve of a coating substrate sample, where the coating is faster. Sorry, this is the substrate. The low frequency is the substrate. Here, the substrate is faster than the coating. So, and by doing this experiment, you can play with the wavelength, and you can obtain waves at different frequencies, and okay, you get all the information. This is again, okay, the setup. Okay, nothing new here. Yeah. Here it's shown how you can play with the angle to make with different gratings. And actually now I can say something about homodyne and heterodyne. This is so-called transient grating setup. So it's a grating because laser beams. It's transient because it's pulsed. It's also called impulsive stimulated scattering. Okay, why? Because the setup is as follows. The pump beam is going to a phase mask, diffraction grating. So here it is split in two beams. The beams are joined again on the sample, so there they are crossed. That's for the pump beam. So it's making this periodical wave package, spatially periodical wave package, which, when it is an acoustic wave, it's converted in a temporal periodical wave package. Now, the probe beam, what is the probe beam doing? It's following the same path. So it's again, it's split by the diffraction grating, and there are two probe beams which are crossing on the sample. It doesn't matter that they are crossing, but they are both there. One probe beam will reflect, of course, but it will also diffract a little bit. Because if you have a periodical ripple on the sample, or a change of refractive index, you have some diffraction. That counts for probe beam 1 and also for probe beam number 2. Probe beam number 1 will, so it will reflect, but it also will partially diffract and go back all the way, and in the end, because of the beam splitter, it will arrive at the detector. If you detect this probe beam intensity, if there's no wave, there's no intensity, because there's no ripple, so no diffraction. Only when there's an acoustic wave, there's diffraction. When the acoustic wave is starting and ending, you will have the probe, this intensity of the probe beam, diffracted probe beam. It will go up as long as the acoustic wave is there. If the acoustic wave is disappearing, it will go down and finished. Yeah? So you will see a signal which is going up and down and finished. This is called homodyne diffraction. You are only using one probe beam, and you are using the time evolution of the diffraction. Yeah. There are two parts. There is an acoustic part, so the wave which is passing, and there's also the thermal part, the thermal expansion, which is taking a long time to disappear. And it's the interference between both, between this static diffraction and the dynamic diffraction, because of the acoustic wave, will give some beating. And so even the homodyne signal will give you some oscillations due to this interference between the thermally and acoustically diffracted light. Yeah.
In your system, do you need to, what is the quality of the lenses? Lambda over 100, lambda over 10?
Ooh, we are poor, we only buy
Simple
ordinary lenses, yes.
Okay.
What can be important if you want to use very high angles,
Okay.
you have to be very careful with spherical and chromatic aberration,
Yeah,
because typically the pump and the probe have different wavelengths. So in our lab, because we are so poor, we can only go down to 5 microns wavelength. But in principle, you can go until the diffraction limit, if you, or even half. If you cross laser beams like this, you can, and you can use mirrors instead of lenses to have
to avoid the
better
dramatic
heterodyning.
expression.
Yeah. Okay, I have to speak about heterodyning, because until now I was only speaking about the probe beam, which was diffracting. But you have two probe beams, and the nice thing about this configuration is that the diffracted probe beam, actually, it's collinear with the other probe beam, which is reflected. So diffracted and reflected. So now what you have is that you have interference between a strong reflected beam, because it's a strong probe beam, and of course a weak, because diffraction is very weak, diffracted beam, and they give a beating. And so when you mix a weak beam and a strong beam, it's called heterodyning, and also the changes of optical phase of the weak beam are amplified, and you get more sensitivity to displacement. Yeah. Of course, you also need stabilization, because, you don't need stabilization, but you need a more stable setup than for homodyne diffraction. The nice thing about having this reference probe beam is that you don't have to look for the diffracted beam because it's so weak. You just put your detector in the reflected probe beam, and you know that this is where the diffracted beam will be. So it's very easy to set up, to align. So heterodyne diffraction, and so the signals, as I said, they look like you see there in the movie. Okay, now some applications before I go to full field. Yeah. So with this local probe, you can already do a lot of things. Yeah. I will go quickly through the application, but just to give you some idea. For example, steel. Okay, if you harden steel, make it more hard, for example, for the gearbox of the car, Renault, Peugeot, Citroën, yeah, in France. You can you change. Actually, what you do is you heat up the steel and then you cool it quickly, and you have a change of microstructure. And the more fine are the grains, the more harder gets the steel. Yeah. So there's a link between the size of the grains and the hardness, which is interesting for the industry. The size of the grain is also determining the amount of scattering of the acoustic waves. Grain sizes are of the order of micrometers, smaller or bigger than micrometers. So, and acoustic wavelengths, if you are enough high frequencies, they will scatter. You will have kind of Rayleigh scattering if the acoustic wavelength is much longer than the grains, and you will have other kinds of diffusion even when the grain is as large as the wavelength of the acoustic wave. Or if you play with the wavelength, as we can do by changing for example, the crossing of the laser beams, we can do a kind of spectroscopy of the scattering. Yeah. Signals look like this. Yeah. So thermal expansion and then oscillations. If you look carefully here, you see two oscillations. You see a fast one and a slow one. Yeah. Because if you excite with the laser ultrasonics, if you excite a sample, you not only heat the sample, but you also heat, because of thermal diffusion, the air above the sample. So you excite two waves, the Rayleigh wave and the wave in the air. Again, for our Dutch friends, the Scholte wave, yeah? Or Scholte-Stony for our English friends. Or once I met a Russian and he said, no, it's Scholte-Stony Gogaladze. Because usually there's an unknown Russian which is also has invented already some years before. So all Europe was contributing to this talk. Then these figures are too small to see, but in that figure, what is supposed to be shown there is the different parameters that can be extracted from these signals versus the different grain sizes here. And those were like cut from a sample, from a hardened sample. So for example, the modulus is changing. The modulus which can be extracted from the speed of sound. The thermal diffusivity is changing. The finer the grains, the smaller the more scattering, the more thermal scattering, phonon scattering, so also thermal scattering. The smaller the thermal conductivity. The damping of the acoustic waves. Maybe not damping, but scattering, which is converted to damping effectively, to attenuation, is there. So you can measure all these properties, and so you can have a kind of non-destructive or evaluation of samples. This graph is showing how the scattering efficiency, or how the attenuation is going with the scatter size. Fuel cladding, so nuclear power stations. Why laser ultrasonics there? Because when you want to test the quality of the fuel cladding, actually the people want to test the coating on it, the quality of the coating, because it's important against corrosion. Yeah. I'm from Belgium. Our nuclear power stations are getting old, as our Dutch friends know, because they're living very close. So laser ultrasonics is a quite useful technique to non-contact, because you don't want to go close, of course, test them. And piezo ultrasonics is still contact, so laser ultrasonics in principle is ideal. For example, here, if you put the fuel cladding in a so-called hot cell, like completely shielded from the environment, but you can still send by fibers light into the sample, you can detect the sample on a distance. And the speed of sound, the speed of the Rayleigh waves tells you something about the quality of the coating. People are using different kinds of coatings, yeah? So that's what we try to prove, that you can do it. So in the next slides, I'm showing some dispersion curves, some thermal diffusivity as a function of wavelength, which are all parameters that are linked to the quality of the coating. This sample was rough, or this kind of samples is quite rough. We used here beam deflection as a detection, and actually we were scanning around until we found a good signal, and then we took that signal to do our analysis. So this was quite time consuming, yeah. Which is maybe a disadvantage, but with Fabry-Perot interferometers it could be done probably in a faster way, a better way. What you see here, for example, is a signal as a function of position and time. You see these periodicities there, yeah? That's because of the acoustic waves. You see that from this we have taken the Fourier transform, so you get the dispersion curve, and from that you get the properties of the coating and the substrate. If you look on a much longer time scale, and you take only a Fourier transform in space and not in time, then you see that there are different periodicities, different wave numbers in space, which are disappearing in time. So those are the thermal gratings, which are disappearing in time. Why plural? Why do I say thermal gratings and not grating? Because the excitation here was with a grating. Because if you use these commercial diffraction gratings, they give you first and +1 and -1 order diffraction, but they also give you higher order diffractions, and that's why you have actually in one grating you have more than one wavelength. You can block it or use it. In this case we used it to have in one signal many informations, and so from this we got the effective thermal diffusivity of such a coating substrate samples, which gives you information about the quality. You can do mapping. You can scan the sample and get a kind of quality picture of the sample, and you can plot it in different ways. This is an example of where you are stuck. For example, when against what I was thinking, I thought always oxide is bad for steel. Sometimes oxide can even protect steel, as in this case, in this kind of nuclear reactors. It's protecting the steel against lead, which would otherwise penetrate the steel. So here you see that we have measured points on the dispersion curve, but the increase of the dispersion curve is only at much higher frequencies, and we were not able to measure there. So in this case it's quite difficult to get here. This is information about the substrate, but to have information about the coating you have to go much higher in frequency. So and that requires very fine gratings, and this was difficult in this case. So it doesn't always work. Sometimes it works. Here, this is an example of a polymer on steel. So people were interested in the adhesion, and to estimate the adhesion you have to know the elastic parameters. By the way, adhesion is changing the acoustic wave propagation, so you can try to detect it by looking at the wave propagation. Same story, dispersion curves, elastic parameters. I will go fast. You can also do it for films. This was for rubber, which is quite challenging because it's so attenuating. In rubber plates you have these Lamb waves. Yeah? They are modified because of the attenuation. Again, you measure position time dependence, you take Fourier transform, you get a dispersion curve. If you look at the imaginary part you get attenuation information, and so you can characterize materials. This is very thin. This was when you in microelectronics, when you put solder on copper, I mean here and there you have to solder. The solder is a little bit penetrating into the copper, and both are melting a bit. So we have an alloy between this was tin solder. You have an alloy between the tin and the copper. So you have a multi-layer system, and the goal here of the experiment was to characterize this very thin layer of alloy between the tin and the copper. Actually, the thin layer of alloy was even consisting of 2 layers. So it's really a multi-layer system. Here we did a kind of parameter study to show how sensitive or unsensitive we were to the different layers, parameters, a measurement, and fitting analysis. And so we could show that even for how much? The thinnest layer was about 100 nanometers, that we can actually extract information, provided you have some a priori information about the other layers. Ideally, because of this frequency or wavelength dependent penetration depth of the acoustic waves, you can scan the sample in depth. Yeah? If you have all these frequencies, the dispersion curve can give you the information about the depth dependence of the elastic properties. But you can imagine that if you have like such a continuously changing sample, that theory becomes complicated. What we did, we approximated the sample by a multi-layer. We calculated signals, many. We assumed a lot of possible profiles in the sample. We calculated all the dispersion curves, and we trained a neural network. We trained a neural network to recognize from the dispersion curve the depth profile of the modulus. These are some examples of profiles and dispersion curves. And from that we tried to use the neural network, to use an experimental dispersion curve in order to get the profile of a real sample. Why to use laser ultrasonics to do that kind of things? Because you can also use X-rays. You can use X-rays to, I have to say which sample. This was a shot peen sample, which is a sample in which they add compressive stress to make it stronger. Why? Because when the components are used in practice, there is often tensile stress. The samples are pulled, and so you can break them by pulling it. You cannot break them by compressing them. So by adding some additional compression, when you pull them, they actually go to normal. So they never go. You make them stronger by pre-compressing them, and you can do that by bombarding them with these small balls by shot peening. So, but the shot peening only helps at the top because that's where the balls are impacting. So people are interested in how deep is the profile of the stress. Now, acoustic stress is slightly changing the speed of sound, not much, but a little bit, and that's because it's changing the distance between atoms, and that's what you measure with X-rays. So this is the stress converted from X-ray information as a function of the depth. So our attempt was to try to measure the depth dependence of the stress via the depth dependence of the elastic modulus or the speed of sound. And these are some simulated examples where you see dispersions of velocities and then calculated neural network recognized profiles. And you see that the recognized profile is quite similar to the real profile. Yeah? Those are simulated examples. This is a parameter study where you can see different profiles and different dispersion curves. So you see that the profile has effect on the dispersion curve, but you can also see that it's a bit ambiguous. Maybe maybe two different effects on the profile will have the same effect on the dispersion curve. It's a bit tricky. So it's a bit ill-posed problem. But nevertheless, you can do, with some advanced information, you can have reconstructions. Okay. Now I switch to samples that are from the semiconductor industry. They are all on top of silicon, and silicon has a complicated but nice feature that it's anisotropic. Depending on the angle that the surface acoustic waves are propagating, you have a different speed of Rayleigh waves or any kinds of waves. So this is the angular dependence. The nice thing is that if you can measure it, you have additional information, because instead of only playing with the frequency and the wavelength, now you can also play with the angle to distinguish between the coating and the substrate, because the coating and the substrate in general, they will have a different angular dependence. So it can help. You make the information more complicated but more rich. Yeah. I told you in the beginning that the name of our lab has changed from Laboratory of Acoustics and Thermal Physics to Laboratory of Soft Matter and Biophysics. So this is why I had to add some bio into the presentation. One example is it's in the battery research. In Leuven we have an institution called IMEC. They make a lot of nice microelectronic samples. So one of the things they are interested is making batteries smaller. I think all of us want that. And one of the ways to do it is to have a higher surface between the electrodes and the rest of the battery. And so by having these complicated structures, and one of the things that people are trying is to use, you are using this black stuff in the batteries, manganese oxide, around this kind of surfaces, very thin. So and they want to know the properties. This is a layer of 460 nanometers, of which we determine the elastic properties. Mainly people are interested in that because of some reliability testing purposes. They want to put some values into COMSOL, and they need values in order to do some tests, some simulations and tests. So this shows that you can, by measuring the angular dependence and the frequency dependence of the dispersion curve, you can get values, reliable values. Diamond. In the case of diamond, what is interesting of diamond, it's very hard. It's the hardest material in the world. But also interesting is that it's a very good thermal conductor. It's the best conducting material in the world. One of the dreams of the people in microelectronics is to use diamond to heat sink, because silicon is a very good thermal conductor, but diamond is a better one. And as we know, one of the challenges in microelectronics is to get rid of the heat, because the frequencies are high, the power consumption is too high. So you want to evacuate the heat, and then in the end you want to cool it. So diamonds could be potentially a potential layer that could be used for heat extraction. Diamond is a bit slow to make, so that's why typically the layers are very thin. And so in this research we investigated how good can diamond help to evacuate the heat. We measured also the modulus, as you can see here, because here I show the surface acoustic wave velocity. So from that we get the Young's modulus this thin 800 nanometer diamond layer. But so we also measured this effective thermal diffusivity. As I shown in the beginning, if you play with the wavelength, you play with where the heat is diffusing, and so you can distinguish between this is the wavelength, so the long wavelengths feel the substrate, feel the silicon, and the short wavelengths feel the diamond, and so you have a kind of this thermal wave dispersion curve. Now, what do the people hope? They hope that if you add diamonds, you increase the thermal conductivity, but what we see here is the opposite. The diamond thermal conductivity is lower than the one of silicon, because the short wavelengths are that's lower. Why? Because of this grain structure. Inside of the grains, the thermal conductivity is very high, but at every grain boundary, just like acoustic phonons, thermal diffusion is scattering. So you have scattering of thermal diffusion, so it doesn't work. Diamond in this case does not increase the thermal diffusivity. I will skip this one because I see that the chairman has arrived.
Since we started late, you maybe have 5 minutes.
Okay.
We also need to save time for.
Yeah. I will just scroll maybe through some full field imaging schemes. So in full field, you are working with a slow camera, with a slow CCD camera, and still you want to look at fast phenomenon. And for that, you make use of the fact that your probe, that you have perfect control of the pump laser, which for example is pulsed, and the probe laser, which is also pulsed. So you are illuminating the sample when you want. Even if the camera is slow, it's only getting light from the sample at the moment that you choose. So it's quite simple. You are using stroboscopy to use a slow camera to look at these fast waves. You can do it in frequency domain by playing with the timing between a periodical pump and a periodical probe, or you can do it in time domain by timing also a periodical pump but with a transient signal and a periodical probe, and you change the delay time between the pump and the probe. In our lab we were typically using an electronically delayed probe laser of nanoseconds, in order to control the time between the pump and the probe. If you do that, you collect different images which corresponds to different delay times, and after which you put them together and you have a movie. The limitation of CCD cameras is mainly in the dynamic range. Ideally, you want to, for example, I spoke about picometers. So a picometer, if you put this in a microson interferometer, it's 1,000 times less than a nanometer, and it's 100,000 times less than the wavelength of light. So it means the change of intensity that you get in an interferometer because of acoustic waves results in a change of intensity of the interference pattern of the order of 10 minus 5, 10 minus 6, if you're lucky 10 minus 4. And that's a challenge for a camera, because a camera is limited in the amount of electrons that can be stored on a pixel. So if you have, for example, if you only have 100 electrons and you have a change of intensity of or photons, because every photon can excite 1 electron. If you have a change of intensity of 1%, this will be 1 electron. But if you have a change of intensity of 10 minus 6, this will be a part of an electron which cannot be measured. So the limiting factor of CCD cameras is the so-called, how's it called? The full well capacity, the amount of electrons that can be stored on a pixel. So okay, that's a limitation, but nevertheless, in some cases, things can be detected. For example, there was a question about chirography. It's a pity that I'm running out of time, but chirography is a very nice speckle-based technique, together with speckle interferometry, in which actually every speckle is an interferometer. Every speckle can change from dark to light depending on how the sample is moving in this location. So you just have to do some tricks to convert, to let's say combine all these speckle informations into one consistent image. So here you see, for example, a periodically excited sample, and you see that there's something weird there. Here, that's a defect. Yeah, this is not laser ultrasonics. This is just vibration ultrasonics. Photorefractive interferometer. It's a beautiful, rather new technique. Okay, new means the last 15 years before your PhD started, but nevertheless not so old. In which you are using a photorefractive crystal to stabilize the interferometer, not only the dynamical vibrations, but also the roughness of the sample. So it works fast, it works with rough samples, and you can even tune the frequency. So it works like a microphone, but with some kind of optical stabilization. Sorry, I'm going fast here. But what I wanted to show is that by putting simply a Pockle cell into the, not here yet, sorry, yeah, here, by putting a Pockle cell in the reference beam, you can choose at which frequency the interferometer will detect vibrations or waves. So it's a kind of tunable filter, an optically tunable filter. For example, if you want to detect waves at 1 megahertz and you don't want to be disturbed by the rest, you modulate the Pockle cell at 1 megahertz. If you want to see 100 megahertz, you modulate the Pockle cell at 1 megahertz, 100 megahertz. So you can use it as a tunable filter. So it's really nice. And if you use a camera and you use a kind of stroboscopic scheme, you can make movies of rough vibrating samples and only select one frequency of vibration. But you can also use it, sorry, I'm going too fast, I know, but you can also use it to look at transient waves. This is a slow down movie, this is a surface acoustic wave moving at 3000 meters per second. So you excite it here in this laser destroyed part of the sample. But you see that there's a plane wave moving, and of course you can imagine that if you can make such a waves, you can see interactions when they meet some defect. Even when it's under the surface, it will feel it, yeah? And you can use it for non-destructive testing. Non-destructive testing. Here you see on the left, you see that the wave is encountering not completely hidden hole in the sample, yeah? And you see some circular wave appearing from it, yeah? This is a wave made by a circle pattern, yeah? So you have circle waves. These are waves on membranes. These are simulations to show how waves are interacting with defects. This is nice. This is a hidden hole here. So the wave is excited here and is traveling over the hole. In this case, we could not see anything on the top surface. But if you look at wave propagation here, these are snapshots of the wave propagation. You clearly see the interaction of the surface wave with the subsurface defect. And you can even see like membrane modes, like this membrane here. This membrane is having nice vibrational modes. By doing some Fourier transforms, you can get that, and you can even get the dispersion curve and the elastic properties of the membrane. These are some references, and these are some acknowledgements of people who have contributed. I mean, with whom we have been collaborating. For the best beer, you have to be here in Leuven. And thank you for your attention.
Okay, well, thank you very much. I think we have time for a few questions. Yeah.
I was wondering whether due to thermal motion there is an elastic permanent wave field that exists in any material. Are we far from being able to measure this permanent elastic field with interferometers?
Do you mean the thermal expansion?
No.
No.
thermal motion that create waves.
Ah,
plastic
spontaneous, like in spontaneous Brillouin scattering.
waves. Yeah, something like that.
Yes.
But from an imaging technique, would it be possible to
Aha,
observe?
like time resolved spontaneous Brillouin scattering.
Maybe not time resolved, but to have an idea of these natural vibrations due to thermal noise.
Yes.
Or is it too small to be measured right now?
Right now or forever maybe. It okay, we would have to estimate, like let's say from KT, to what displacement this gives rise. I don't have numbers in my head.
Me neither.
I would estimate that the optical noise is still bigger than let's say than the optical path change due to those. Well, no, it's not. No, the fact that spontaneous Brillouin scattering can be detected, but it's slow. Huh? You need some seconds typically to get some information. Yeah. No, it must be possible. Let me think about it.
Okay.
I have a question about the full field techniques you presented. How do they compare in terms of acquisition time? How long does it take to get one image, especially if you have to vary the frequency and get one image at a frequency at a time?
Yeah. Let's say they are. Where was it? Here. So how do you say in English? You gain something, you lose something. Yeah. What you gain with full field is you have all these pixels at once. For example, you have 200 times 200 pixels, which is a lot. You gain a lot in space, so that's time you don't have to spend by scanning. Because if you want full field by scanning, you have to scan all the way. But what you lose is that to acquire, okay, the examples I showed, for example, we needed some repetitions. So we needed, let's say, depending on the repetition rate of the laser. Okay, let's say ideally you only need one frame, one laser pulse to have an image for one delay time at 10 Hertz repetition rate. So then you would collect one delay time per 100 milliseconds. So you would collect 10 delay times per second, ideally. Yeah? But in, let's say, scanning techniques, if you have one oscilloscope trace, you have like 30,000 points in 1 second. So you gain in spatial dynamic range, but you lose a lot in temporal dynamic range unless you measure for very long times.
Yeah. But the purpose is to have a large image, not time resolved, but at least one image quickly.
Yeah, you have, yeah. Or for example, if you're only interested in a few times, not in all the frequency spectrum, in a few times, then it's can be quite convenient. But again, the sense, well, maybe some advertising for our colleagues from Nottingham. They developed a camera with a very high pixel amount of electrons per pixel. So they can have a very high dynamic range, and they can even do lock-in detection on the pixel. Every pixel is a lock-in detector. So there is some evolution that even cameras will become very fast.
Yeah.
In your opinion, which technique is the best to see like a displacement less than nanometers?
For a rough sample, or for
well, for both, so like a rough sample and a polished sample.
And in which frequency range? Yeah, because okay, yeah, I think we have to know the answer to every question, and then there will be one or two that will be suitable. I think I don't have a preference for one particular one. Like recently we got a new person in the lab and she brought some samples and we tried all of them and nothing works. Sometimes, I mean, for example, we have in our lab we have a commercial laser Doppler. It's perfect usually, but okay, you cannot go above 20 megahertz. So then you have to go back to the other techniques which don't work well on rough samples. So it's from your lab, maybe the answer you want to hear is that the speckle knife edge detector from Nottingham. I think can work for many samples. That's true. Not full field, but scanning. Very nice approach.
Okay, let's thank speaker again.